Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I am going to explain you a new paper called Improving Noise Robustness of Automatic Speech Recognition via Parallel Data and Teacher-Student Learning. So this paper is by a collaboration from BUT, Brno University of Technology from Czech Republic, and then Amazon voice recognition team. So this paper is by many authors, as you can see the authors here, and the overview of the tutorial is going to cover the overview of the paper first. Then we will see what is the proposed method. Then we'll see the experimental setup, and finally we'll see all the results published in this paper. So first let's see the overview of the paper. So basically this paper is written for noise robustness for speech recognition. So basically this says how do we improve the current speech recognition accuracy in the case of noise conditions, and this paper uses parallel data and also uses teacher student learning technique to improve the speech recognition in the case of noise, in the presence of noise. So they also use something called Logit selection method to reduce the bandwidth during transferring knowledge from teacher to a student, and this data is used this paper uses data set from Amazon. Basically they have collected call home data, not call home data, so the data which is collected using far field conditions. For example, let's say in Alexa we speak, right? Like in the Alexa will be there and we speak, okay Alexa, and we ask it to do some task. So that data is a distant speech recognition data set, and they have used 8,000 hours of data set. Basically only 800 hours of out of 8,000 hours is transcribed, and remaining is untranscribed, and we'll see how they are making use of that untranscribed data also during student network training. And finally they show that sequence based training of teacher student network gives the best accuracy, and then they show that no, instead of just training with multi style based speech recognition, which basically mixes noisy data with clean data and trace the network, they use teacher student network, and they show that this gives better accuracy compared to only training with multi-style based trainings. So the proposed approach basically has, as I said, it's a teacher student learning approach. So basically you have a teacher network, which is a neural network, and you have a student network. And historically when people use teacher student network, they basically keep a large teacher network which will capture a lot of information from the data, and they keep a small student network which is basically going to learn from the teacher network and with the other data set. So but here they use similar architecture. We will come to that later. So basically they have a teacher network, as you can see here, this one, and they have a student network here, and they use, so once they train a teacher network using clean data, as you can see, I'll come to the details. So once they train a teacher network using clean data, they try to transfer knowledge from this network to the student using noisy data. So basically that whatever data they have, they corrupt it using noise, which is called data augmentation here, and they take the softmax logits, basically the softmax output, like the probability values, and they use that as the ground truth, and they try to minimize the KL divergence between this predictions from teacher and the student. So basically what happens is, essentially when the network is trained, when the network tries to minimize the KL divergence, you are trying to match the distribution of the student network, basically the probability distribution of the student network, to the probability distribution of the teacher network. So that's how when you are reducing the KL divergence between these two distribution, they come closer. Basically the student tries to mimic the teacher, right? And you use that KL divergence signal or KL divergence loss as the loss function, and you back propagate by differentiating that KL loss, and you update the networks. right? Basically you will not update the teacher network, basically you will update the student network. So this is how the whole setup is. You have a teacher network, you train it with clean data, then you want to train a student network with noisy data, where you take the softmax logics from the teacher network as the ground truth and tries to minimize the KL divergence between the probability distribution of the teacher network and the probability distribution of student network, and you train the model, train the student network using that loss, right? So that is the whole idea. So as I said, basically the teacher student training is for like sort of domain adaptation. So you can think of this as let's say your clean data, where your clean data, which is X clean, you can see in this as some distribution after the teacher network is trained, and which is let's say this is domain 1, and when you have this noisy data, which you can call it as domain 2, and when you minimize the distribution, the probability distribution of the domain 1 and domain 2 using KL divergence, so they should come together, right? So that's the idea. So so first, as I said, the teacher network is trained with clean data, and then you create the noisy data using, or you artificially create the noisy data version of the clean data, adding noise, different sorts of noise. Then after you train the teacher network, so you get seen on probabilities. Basically the probability outputs what you get is the seen on probability. So seen on is sort of, you can think of it as a phoneme. It's not exactly phoneme, it's some sort of phoneme. If you read more about speech recognition, you will know, like hybrid approach of deep learning, hybrid approaches of speech recognition, you will know what is seen on. So seen on probabilities are sort of probabilities distribution. You take that and you also compute the seen on probability from the noisy input to the student network, then you try to minimize the KL divergence between these two distribution. And so that what you will do is, once you minimize this KL divergence, the behavior of the student network should be similar to the teacher network. So once you are able to minimize the KL divergence. So and that is the first technique, using teacher student network training or teacher student learning sort of approach. Then they introduce one more technique, which is called Logit selections. Basically this is also one very well known thing in transfer learning or in teacher student learning. So basically the Logit selection says you want to keep only the logits, or only the hidden values which have highest probabilities. So basically what it means is, so let's say here we are getting probability, softmax probability, right? So here we are getting a softmax probability after this LSTM layer. Then so, and we know that the probability of C known is given the clean data is, you can calculate it with softmax equation. The only change with this equation is there is one capital T here, which is called temperature coefficient. Basically this temperature coefficient, if you make it as 1, which is going to be as similar to the normal softmax, but you can change this temperature coefficient to see like how the behavior of the model is. But let's assume this is the probability of the seen on SI given the clean data frame, clean input frame. So what is the idea of Logit selection is, you want to select the k highest Logit values, okay, and the k highest Logit values whose indices lie in the set capital K, right? And you can see we are going to keep only those k highest probabilities, and we are going to remove, or we are going to make all other probabilities as zeros. So as you can see here, right? So that is the idea. So that's all it is. Like you have a teacher student network, but the one more important thing you will introduce is a Logit selection thing, which is going to be, I mean, as I described here, is going to be like keeping the k maximum probabilities and remaining making all other probabilities as 0, right? And for the network training, so we'll see the experiments and results here. Like basically you have a teacher network and student network, right? So teacher network and student network, usually what people do, people keep bigger network for teacher training and a smaller network for student training. But here in this case they are using same same teacher and same student network. Basically it's exactly same architecture, and you will see the weights are also taken from the teacher network only. I will show you. So basically the student or teacher network is a 3 LSTM layers. Like stacked one on top of each other. So at every timestamp, say after 3 LSTM layer, we have one more layer, which is basically the softmax fully connected layer, which computes the probability over these many number of genomes, 3010 genomes, right? So basically you can think of it as like every frame will get, let's say you get a frame and that will be classified into one of the three one of the 3000 genomes. Basically you will get, for every input feature vector, you get the probability vector, right, the softmax vector. And the input consists of 64 dimensional feature vector of log mel filter bank energies, and those are going to go as input to this LSTM layer. And as we know that this is basically, this data, as I said, this is sort of far field speech recognition data. They have collected around 8,000 hours of beamformed speech recording, out of which only 800 hours of data is transcribed and remaining is untranscribed. So basically what they do, they take this 800 hours of speech data, which is the transcribed data, and they train a teacher model using that 800 hours of so 800 hours of transcribed data using supervised method. Just like you just want to classify all this 800 hours of data into, basically the teacher network takes that 800 hours of data and predicts phoneme or cenones for every frame, right? So that's the idea. Then that is the teacher network training. So then what you do is you take every utterance and add one of the 3 additional noise sources. So basically the noise sources are room impulse responses and reverberations, which are run from 500 to 900 millisecond. Then different noises are added, different signal to noise ratio, you can, like from 0 to 30 dB. So that is the training data, and for the testing they are using 3 different test data. So one is the clean data, which is like completely clean, no noise or anything. Then they have a noisy data, which is basically the noisy version of the clean data. Basically they add artificial noise to the clean data and they create a noise data, right? Then they have a realistic noise data. Basically this is like playing, for example, let's say you are collecting the data in a room, you play the multimedia, you play some audio recording, and along with that you record the audio. This is like sort of a realistic condition where you are actually collecting the data in real noise condition, unlike the second case where you are artificially adding the noise through some computer program, right? And coming to the results, they have many experiments here. So basically the baseline model is basically a teacher network, which is going to be trained using supervised method for this 800 hours of clean audio data. And as you can see, don't worry about this 0.0, because this is basically, this number is basically the relative error rate reduction, and since you are testing with the same things, 0.0, don't worry about that. Then that is for the baseline. This teacher network trained using the 800 hours of supervised or 800 hours of labeled annotated transcribed speech data. And they have another model where you can take the audio data, which is basically the clean data, and add noise to the clean data and augment that 800 hours of data with a noisy 800 hours of data. Basically this is sort of multi-style training where like for example, if you read the deep speech papers, where they add a different sort of noise to the clean data itself and they augment the data, right? So with different noise types, like for example speed perturbation, volume perturbation, then there is a noisy perturbation, so many perturbation techniques. So you do the perturbations to the clean data and you train the model using both clean and noise data together. That is called multi-condition training or multi-style training. So that training is a second model they have built here. So basically what happens is, what should essentially happen is, the accuracy should improve. So basically here, compared to this, in the clean data you are not getting that much improvement. It's just like 0.5% error rate reduction, but you get a lot of improvement on noisy test data, because you are already taking care of this noisy distribution in the training itself using multi-style training. So that's why you get a little bit, good improvement over basically this negative improves it's a reduction, right? So basically you are getting relative 15% improvement, right? So the 15% improvement you are getting on the noisy data, and in realistic also you are getting fairly around 4.26 relative error rate reduction. And so what happens but the problem with this multi-condition training is it is giving improvements over the noisy data and realistic test data, but it's not giving any improvement over the clean test data. As you can see here, it's actually worsening the performance. It's not negative, because you can see it's a positive number. Basically, it is becoming a little bit bad over a clean data, but it's becoming good over noisy data, which we don't want, right? We want the improvements over both noisy and the clean data. So people argued about it, and they started using this student teacher training. So where you can see here, so here they have a student where the temperature is set to 1, and they have a parallel corpus of 800 hours, which is basically generated using noisy augmentation. Here you can see you get a improvement of 2%, right? Because it's negative, you can see here. And also you get better improvements over noisy data, noisy test data, right? So it's minus 17%, which is good. Then on the realistic test data also, you are getting very good improvement. This is actually a very good cue that you can using teacher student learning is better approach compared to doing multi-condition and training, right? Many people today, even me, I mean many times whenever I train speech recognition engines, what I do to take care of these noisy conditions which occur in videos, multimedia content, whatever YouTube content, YouTube videos and stuff. So what I do, I take the clean data and I augment it with noisy data. So which is basically historically proved that it's going to work better, or which is going to capture the distribution of the noisy data, so that our even it works in the testing conditions also. But what these guys are showing is that's what even I knew till today, what I was doing till today. But what these people are showing is, if you do teacher student training, you can get actually better performance compared to only doing multi-condition training, right? So which is actually a good sign. So that's what they are showing here. So you have a student network with temperature set to 1, and it's actually beating the multi-condition training. Then they can also change the temperature coefficient, which basically it's the capital T symbol you saw in the softmax equation. So basically you have a student with T equal to 2, basically the temperature is set to, and the same data they use for training, but this time you are getting a little bit lower accuracy. So basically this says if you use temperature T equal to 1, you get better performance, and making temperature T equal to 5 is actually worsening the clean data set, clean test sets accuracy, which is basically become positive, right? This is actually a good sign. This is one result, and they have a second result where they are finding out the relative error rate reduction using the Logit selection techniques. So here 5, 20, 40, those are all the Logit maximum number of Logits they are going to select. And as you can see here, basically they are also plotting the error rate reductions with respect to the temperatures 1, 2 and 5. And as you can see, for 40 capital K, where basically the 40 units of selections, 40 Logit selections technique, the temperature 2 is a very good, and for 20 is also the temperature 2 is very good. And if you increase the temperature to 5, so all the models are becoming bad, right? And same thing with noisy test data, and they show 40 is better, and here they show 20 is here they show for realistic test data 20 is better, right? Then also they have at the end they have one more plot where they actually increasing the training data. So as you can see here, when I'm say training data, increasing the training data, you can ask me a question. You had only 800 hours of transcript text data. How did you increase the training data? You can ask. There is some small trick here. If you can see here, let me show you. If you see it here, if you think of this network, do you think you need any ground truth text? When I say ground truth text, do you need any labeled or transcript text data? The answer is no. Why? Because we are not computing the error based on the ground truth transcript, right? We are actually computing the error signal using the logits or using the probability vectors from the teacher network. Basically, once I train the teacher network, I can feed any audio here and get the probability of or distribution over the teacher, distribution from the teacher network, right? Then I can feed the same thing to this network and get a student distribution. Then what I have to find is I just have to find the KL divergence, which is very easy. For that I don't need any ground truth transcript. So this way I can increase the amount of training data like whatever I want. Like I have a lot of unsupervised or I have a lot of untranscribed text data. I can make use of that, and I can actually increase for the training of student network. I can increase the training data by a lot, because you have unsupervised data, which is going to be good for unsupervised. I mean, this is going to be helpful for this model, right? So as these guys are showing that if you increase the training data, you get actually a very good performance on the clean test and the noisy test and on the realistic test set, right, which is actually very good. So this is sort of like use a small set of data for training the teacher network. Once the teacher network trains something and learns something, then you use all the unsupervised or untranscribed data for training the student model, which is going to be better at capturing all the information, right? So this is it. Then you have the last, we have one more last result where they are showing they're showing how to make use of sequence level discrimination criteria. For example, in our last case, whatever we saw here, we were calculating the KL divergence at every frame level. Basically, we are going to feed one frame to the network, then we get one probability score, right? Basically, one probability vector, which is softmax distribution over the cynons. But what people have shown historically, that if you have a sequence data and you should apply sequence level criteria instead of applying frame level criteria, then the model will learn the model will capture the previous frames information also. Basically it learns the temporal information. So for that they have used this MBR, basically the sequence level minimizing the Bayesian risk technique, which is introduced by Daniel Povey back in I think 2009, if I'm not wrong. So they are using SMBR, which is basically sequence level criteria, sequence level loss function, minimizing Bayesian risk, and they actually get pretty good results. Basically, they beat all the other models using this after augmenting with the untranscribed data. Basically, they have 6 into 800 hours of parallel data and 800 hours of noisy data. It's basically 6 into 800 when I say it's sort of taking the untranscribed data also, and they're using both cross entropy and SMBR, which is sequential minimizing the Bayesian risk objective, and this cross entropy objective. Combining them together, basically you get best model. Best architecture over all of the models they have described here. This is sort of like this is the best system, basically the best system over all the other models they have shown in this paper, right? And that's it for this video. Thank you so much for watching. If you're not subscribed to my channel, please subscribe for more content. Thank you.